Hello guys, I'm Boyd. Today I'm gonna talk about how you can utilize CodeQL to discover vulnerabilities and do variance analysis. So hi again, I'm Boyd from Taiwan. I'm currently the security researcher at SiteCraft, a member of ChangeRoot, a private security research group in Taiwan, and a programming lover. So here's the agenda for today's talk. At first, I will briefly introduce the background knowledge and the terminology of CodeQL, including some basic features and examples. Next, I will demonstrate how you can use CodeQL to discover vulnerabilities, to find things you are interested in, and to be helpful in SDLC. And lastly, there will be a conclusion to sum up today's talk. So let's get started. So, what is CodeQL? I believe that many of you have heard of this tool before, since it's widely used by many security researchers and big brands like GitHub, Mozilla, and Intel. This is a brief overview of how CodeQL handles both extractions and evaluation. As you can see, the codebase is extracted by proprietary extractors and stored as a snapshot database. And each database contains queryable data extracted from the codebase for a single language at a particular point in time, which means that if a project uses multiple languages, you can have a database for each language and a copy of the code to display your query results on. Once we get the database, we can then use CodeQL query to get data that we want in many ways. So CodeQL has provided extensive libraries to let you do variance analysis, including static analysis, data flow analysis, taint analysis, and CFG analysis. You don't have to worry about supported languages. CodeQL provides many common languages at a time. Additionally, CodeQL is not a kind of tool that will automatically find vulnerabilities for you. It is a tool that simplifies the process for you. You don't need to prepare the environment and the tools to do this analysis, which is really exhausting. CodeQL benefits you by providing well-organized, extensive libraries to let you write your rules semantically. Static analysis is the most straightforward analysis you would use in the first step of the analysis. It can fetch any static data fast and accurately. It is common that researchers use static analysis to search for hard-coded things, like password, API key, or the misuse of a dangerous function. Check out examples here. On the left, we write a simple query to find all the occurrence of the function, execute, while on the right, we write another simple query to search for hard-coded password. These queries are simple but helpful if you are searching low-hanging fruit and it did return some results back. This one is more complicated. We extend a class from invoke expression, a predefined class in CodeQL, to find all objects that are invocable. For example, functions or constructors. This extended class will try to find all occurrence of regular expressions that contain dot star. Why do we do this? It is because that some developers will write down this regular expression, but want to match the real dots actually. This is a common pitfall for especially junior developers, though seniors might make the same mistake too. Data flow analysis is used to compute the possible values that a variable can hold at various points in a program. Determine how those values propagate through the program and where they are used. Therefore, use this feature will help us evaluate in different points the fate of some malign or insecure data. If data is used in a dangerous way, which will reveal some possible leaks or even impactful flaws. Besides, it can also let us understand other aspects of how a program behaves, and lead us to other intriguing paths, maybe. This query is a lot complicated than the queries I presented in the previous slides, and it is to find interesting functions arguments that are controllable by users. With this query, I'm able to see how a program will behave after receiving my inputs. Taint tracking differs from basic data flow that it considers non-value preserving steps in addition to normal data flow steps. For example, in the assignment, y equals 10 plus comma plus 10. If x is tainted, then y is also tainted, even though there is no data flow from 10 to 10 plus comma plus 10. The taint tracking library is in the taint tracking module. Any taint tracking or data flow analysis query has three implicit components, one of which is optional, and an implicit component. The implicit components are one or more sources of potentially insecure or unsafe data, represented by the taint tracking source class. One or more sinks to where the data or taint may flow, represented by the taint tracking sink class. Zero or more sanitizers, represented by the sanitizer class. A taint tracking or data flow query gives results when there is a flow of data from the source to a sink, which is not blocked by a sanitizer. The last one is CFG Analysis, but honestly, I don't see much about the use case. So if you are interested, you can get more information from CodeQL's page, but I would just skip this one. Now, I will talk about the practical usages of CodeQL. They are literally things that I do every day to help with my research. So the first one, replicate CVEs to find new CVEs. It means that we model out vulnerabilities to find them somewhere in the same code base or other code bases. Firstly, you will learn the vulnerabilities more in details while writing CodeQL query. And after the writing, you will be able to query other projects to find treasures. Of course, it is important to write the query in a general concept, meaning that you should understand the flaw and know the concept of it. This one is actually a real report from HackerOne. Look at these two regular expressions. Could you identify the vulnerability? So the issues stems from the fact that they use dots instead of real dots in these two regular expressions, which will make the regular expression fail to match the real dots in URL. It matches anything instead. It means that once a hacker has owned a domain like totallynottwitter.com, just like the page I show you here, in this case, it can trigger the extension to pop out under the wrong context. We have said that this is a typically suitable case for the static analysis because we want to hunt for static things. Just reuse the code snippets I wrote before and apply to other code bases to see what results we get. After applying to Electron with JavaScript language snapshot database, we quickly identified that there's a same vulnerabilities in Electron code base. Some of you might haven't heard of it before. So Electron is a framework built on top of Node.js and Chromium to let developers write cross-platform desktop applications using JavaScript, HTML, and CSS technology. The vulnerability here affects the same functionality provided by Chromium to let developers load extensions in Electron. And the patch is really simple. Just make sure that all special characters get escaped correctly. Here is another case that I found recently in this year. Due to a penetration testing case, I stumbled upon this framework for the first time. Besides, I noticed that they use an endpoint to serve different types of static files. Not a common scenario. And it works like this. You just provide a base64 encoded string to the parameter, and it will return its contents. It will firstly base64 decode the string to get the real path, and then read the content from the file. After checking all the vulnerabilities it had before, it seems that this library is prone to local file inclusion issues for several times. A good target for various analysis, definitely. In addition to client dependency, this library, the Umbraco forms seems to be a good target as well. Maybe we could try to do various analysis toward it, but we will just focus on client dependency this time. This is how a local file inclusion happened to the client dependency library. It is really straightforward, right? So after sending the payload, we will get the real content of the file, web.config. Okay, so let's model this flow. And because it will take up too much of my time to cover all steps about how I trust the code to find the root cause of these two vulnerabilities, I will skip them then. However, it roughly goes like this. There is a user-controllable input which will be intercepted by the classes implementing iHTTP handler interface. We call them source. There is a weak point that will read content of files and send back as the response body. After reviewing the code, the source code, we know that this weak point is from the function write file to string. So we code it sing. So in this case, Taint Analysis is definitely the go-to. After modeling with CodeQL to find those two old flaws, I could successfully discover a new one with the same CodeQL query with a slight modification. And the modification literally leads me to another possible bypass of this patch. to those two vulnerabilities. The left one is to find all methods that have the qualified name starting with system.web.ihttp handler. Then on the right-hand side, source nodes are set as their parameters. On your left, things are set as the function we mentioned before, the culprit of the previous two flaws. The right-hand side is our extra additional tainted steps. It looks very complicated, right? It is. It is hard to explain all these steps, but it requires a lot of effort to read the source code and figure out under what situation should the nodes be tainted. I want to state it one more time. Don't consider that CodeQL is a tool that will automatically find bugs for you. It needs to be trained and operated by professionals by nature in order to find valid bugs. Apart from finding bugs, we can also utilize CodeQL as a pattern finder. And because CodeQL is cited as a semantic code analysis engine, it is naturally that you can use it to find something that you are targeting. I list some common methodologies that we use in our daily lives. Let's check them one by one. We are all very familiar with this, right? Grab to find something statically, and regular expressions to find something with patterns. Although they are easy to use, they are pretty much vulnerable to false alerts. It is because that this kind of searching methodologies isn't context aware. And second one, UML Class Diagram, is a graphical notation used to construct and visualize object-oriented systems. A class diagram in the Unified Modeling Language is a type of static structure diagram that describes the structure of a system by showing the system's classes, attributes, operations, and relationships among objects. Here are some class diagrams in UML. And a typical case that I come up with is the CVE 2018 1000A61, a Jenkins remote code execution vulnerability. The rationale of this issue is the loose constraint set while doing routing matching and dispatching. You can see it on the slide. The stapler web framework staplers most objects to URLs. Therefore, all we need to do is to find good gadgets to chat all together in order to achieve remote code execution. So yeah, in this case, using UML seems to be a very suitable case. We can leverage the UML to get our head around this challenge. You can clearly see how it could be so useful here. I've said that it gives you extensive libraries to use, so CodeQL could be easily used to find things. Besides, it gives you results based on context, and therefore these results are accurate and meaningful to you. So let me take the Umbraco case as an example one more time. I said that I found a local file inclusion issue that affects client dependency from version 1.8.2.1 to 1.9.8. Nevertheless, in order to achieve remote code execution, we need to find an entry point, but it doesn't require us to be authenticated. So how about using CodeQL to find those pages? We can not only find unauthenticated accessible pages, but have a human-readable query to share to the community. Or we can also keep it somewhere for reference in the future. So once we get a list of pages that we can directly access, all I need to do is to pick up a common page that every copy of Umbraco CMS would have. So /umbraco/pin.sps seems to be a good target for me. Let's try to exploit it. So here is our exploitation. Our very first step is to use the local file inclusion vulnerability to read the content of the file web.config. So after getting the content of the web.config, we can get the machine key to trigger the deserialization vulnerability. So we use ysoserial.net to construct the malicious object, and our target is /umbraco/pin.aspx. And our command, which will be executed, is who am I. Alright, so everything is set up. We execute the payload. So after executing the payload, we can get the output of the command. So our exploitation is successful. Okay, so regression test, our last one. So in this section, I want to talk about SSDLC and how you can apply CodeQL to SDLC, namely software development lifecycle, to make it more secure. SSDLC, aka S-SDLC, is the initialization of secure software development lifecycle. Simply put, add security activities to the system development lifecycle, preferably in every phase of the SDLC, and formalized. If you have heard of DevSecOps, it is actually part of it. So how could developers apply CodeQL to SSDLC? First, we could try to write simple queries to find hard-coded strings, sensitive data, insecure configuration, etc. Then we can gradually rewrite our existing unit test with CodeQL if possible. Or we could also just import a GTM set of rules, especially the security one. Additionally, since CodeQL is a community-driven project, it is also possible to find others well-written queries from public research or GIST. The following are some rules that are grabbed from the LGTM's official report. So this one is to check if there exists any client-side URL redirect in the code base. The LGTM team has used the Taint Analysis to check if a user-controllable input is possible to control to reach the website's will redirect. This is called Open Redirect vulnerability. And this one is to check if there exists any user-controllable inputs that will be read and parsed insecurely by the XML resolver. This often results in XSE injection, XML external entities injection. And this query is the outcome of a public research from Pontester doing a variance analysis against CV 2018-16621. This issue description said that a Java expression language injection vulnerability has been discovered in Nexus Repository Manager 3. We thought that it is a good target for doing variance analysis to find other variants about EL injections. and he did find a different kinds of variants at the end. The journey is fun, and you can learn from him by utilizing the CodeQL powerful libraries to circumvent a variety of limitations. Now we are moving to our last bullet point, conclusion. I know your mind must have been overwhelmed with confusion if you do not have experience using CodeQL before. However, I hope you will start using it or even share your queries with the community from now on. In the future, while CodeQL starts supporting more languages, it can cover a wider range of libraries and code bases, which means that we are able to do variant analysis on more targets and secure more projects. Besides, think of it. CV list is just a bunch of descriptions with no real things to replicate or prevention suggestions to follow in most cases. With CodeQL, however, we are able to model each vulnerability and make each of them generalized by the efforts of the whole community, which is neat. To sum up, CodeQL is a nice tool for finding semantic things, and I am still learning as well. Alright, so that's all my talk. Thank you all for listening. I hope that you will learn something from my talk. Besides, if you have any questions, please leave your questions on Discord channel. Thank you.